Our speaker today is or Talis, as he likes to be called, Marie. He's a PhD candidate at the University of Guelph under the supervision of Dr. Bernard Grodzinski in the Department of Plant Agriculture. Talis has been interested in greenhouse production since he attended college at Niagara Park School of Horticulture, where he visited many greenhouses, had hands-on greenhouse courses, and did an internship at a farm with greenhouses. Since then, he continued learning more about the industry and Canadian agriculture in his bachelor's and master's of science for a BSc and an MSc. He admires fundamental biology and innovations that can bring it into agricultural practice. His research focuses on dynamic LED recipes that entrain the circadian rhythm to grow greenhouse crops under continuous light. His philosophy is to start with a rhythm and then choreograph photosynthesis and canopy architecture. Afterwards, he's looking at continuing in academia to integrate these concepts in greenhouse artificial intelligence and whole canopy modeling. Please help me in welcoming Talis.
Alrighty. Thank you so much. And then where's the mouse? Oh, just here. Yeah. Okay. Perfect. Oh, yeah. Okay, cool. I'm just going to get the laser pointer ready ahead of time. Okay. Thank you, everybody who made it out in person and everyone who's online. I'm grateful to be here to show you some pretty exciting research that I'm just really into. So I'm just going to jump straight into it. So we're going to do a little bit of an overview here. I'll start with a background, introducing the supplemental lighting strategy that this is based on, talking about continuous light stress. And then we do have to get into the fundamentals of circadian rhythms. In part one, I'll talk about these transpiration rhythms that we found and how that's relevant to the plant energy balance in the greenhouse. In part two, we'll talk about another experiment that was done, and we got total biomass, and we did some biomass partitioning, and notice there's some vegetative degenerative balance effect going on, and then the canopy architecture. In part three, I'll give a bit of the vision and future directions. So I'll kind of just start too. We're at the university, in the lab, in growth chamber level. So we're kind of just trying these new ideas that will then eventually be adopted into the greenhouse sector or vertical farms, as I hear there's other industries present here. So we're just trying to crack the barrel on some new stuff here. So the background here, tomatoes and cucumbers, they need about a DLI of 30. However, that DLI drops below 30 from October to March or so. And so it's beneficial to use supplemental lighting. The current trend is about 200 ppfd for 16 to 18 hours, starting at maybe 11 p.m. or 1 a.m. and going into sunset. And this total supplemental DLI is about 13, depending on the operation. And so the strategy that's being promoted at Harrow, so Zhuming did a lot of work on this. You basically want to do a lower light intensity, but over a longer photoperiod so that you can reduce the electricity costs because you're not pumping as much electricity into light intensity. And you're reducing capital costs because you're not going to need as many LEDs to light a certain square footage area. However, like continuous light, it would be ideal. It would be technically, theoretically, cheaper to just supply lower light intensity, getting the same DLI over 24 hours. But that's not the case. So in crops like tomato is the most sensitive. It's like the guinea pig. It gets photoperiodic injury, which leads to yield reduction. And photoperiodic injury has been documented about 100 years ago, so it's not a new story. Here in the lab, under control conditions, we can see that continuous light alone, everything else held constant, you've got a healthy tomato, and then you've got a photoperiodic injury tomato. You see an older leaf in the background has this interveinal chlorosis. And what I noticed, and it's not documented too much, but the younger unfurling leaves, they have a marginal chlorosis and they get quite brittle. And cucumber is, considered to be tolerant in a greenhouse, but under controlled conditions, it also experiences photoperiodic injury. So it's not immune. And if we just could kind of come up with strategies, I think we'll get a healthier tomato plant or a cucumber plant. So there has been successful continuous light strategies that have been published out of Harrow by Jason and Zhu Ming. And their dynamic LED strategy on tomato and pepper, and they also did cucumber, which I'll talk about. The basic premise is you start with red LEDs during the daytime for 12 or 16 hours or so. And then at nighttime, you switch the spectrum and you switch the intensity. So it's a lot dimmer over 12 to 8 hours of that night period. So you have this red day, dim blue night. And that strategy maintained the same yield as control if you would have just lit it for 12 or 16 hours with the same DLI and just had a dark night. But you used less electricity because you're taking advantage of that nighttime pricing. So tomato and pepper, they specifically performed significantly better than just supplying a 24-hour continuous light without shifting the spectrum or intensity at all. So they do a lot better. Cucumbers, on the other hand, they seem to just be more tolerant of that continuous light 24 hours. So you can save a bit more electricity with them. But my question here and what we're bringing into the lab is, well, why did it work? Why did this change in spectrum and intensity work? And the only way to really study that is if we bring it into a lab and we control for all other variables, no temperature fluctuations, no natural light from the sun entering, the greenhouse. There's a lot of things that could influence it. So what if we just did it completely indoors? And there's some literature that was showing that, okay, so like photoperiodic injury, it's not necessarily continuous light that's the problem. It's the disrupted circadian rhythm. And they knew this back in the 50s, even before the term circadian was a thing. And how they discovered that was if you gave them weird hours of lighting, so say 5 hours on, 5 hours off, 5 hours on, 5 hours off, and you just did that constantly, you would develop photoperiodic injury. So it doesn't have to be continuous light to induce it. And that's a very important finding. So that's how we know that it is the circadian rhythm. And what does that do to an organism when you disrupt their circadian rhythm? So you could think about in people and us, when you say you're adapted to the environment here, the day-night cycles, it's ingrained in your kind of rhythm. And if you were to suddenly fly over to another, part of the world, let's say instantaneously, and all of a sudden day is night and night is day, according to your internal clock, relevant to the external environment, you experience jet lag. And that jet lag feeling, like I'm sure we've all worked late at night before, where you're just kind of tired and you're working and you're kind of like, you're barely, you're not as sharp as you could be, but you're able to just kind of function, but you'll eventually develop like a headache and a whole lot of other daily patterns are going to be kind of disrupted. So it's not a good place to be in. And plants and humans, we have similar circadian rhythms, surprisingly. So I'm suggesting that, PI, it's like jet lag. It's an easy way to understand it. And what these dynamic LEDs are doing is they're helping entrain the circadian rhythm. So this would be an acclimation strategy. And following that, so learning more about circadian rhythm entrainment principles, it can improve the dynamic strategy. So we have to go into the literature a little bit on this. So what do circadian rhythms do? They coordinate these internal feedback loops with environmental cycles. So going back to like a human example, you wake up in the morning, you maybe start feeling hungry depending on your circadian rhythm type. But you wake up in the morning, you start getting that hungry feeling, and then maybe you go through some sort of phase, maybe you have your morning routine, and that gets you organized. Then by lunch, you get hungry again, and maybe you have like a little spike of energy. By the evening, you start kind of winding down naturally. By the time you go to sleep, your melatonin starts spiking, and you get into this sleep mode. And so there's a lot of circadian rhythm research on people and our cycles, but it's these feedback loops that they coordinate all the activities with your internal metabolism and your general behavior with your external environment. The entrainment of these rhythms, they need inputs, the strongest inputs being light and temperature. So in a greenhouse, that's what we have. We have a lot of control over light and temperature. So we have a really great ability to control the inputs of entrainment. The outputs, well, that's gene regulation. So the circadian rhythm itself, it's like these, it's a conglomerate of transcription factors and their own feedback loops, and certain photoreceptors and other receptors, they input into it, which then causes a lag or an amplitude, like an increase in a certain gene regulation. And it's very timed. And when the internal cycle, your internal circadian rhythm, resonates with the environmental cycle, like it's just termed in resonance. And that promotes healthy behavior. So here you got your little input, it goes into this clock, and then it outputs gene transcription and behaviors. So jet lag, it's basically you're decoupling all these metabolic pathways. So you make a certain amount of energy every day, and a certain portion has to go to certain organs, and that changes depending on the time of day. The plants are the same thing. For example, like photosynthetic proteins, there has to be an upregulation of photosynthetic proteins that happens and coincides with day length. Obviously, it needs to be ready to photosynthesize during the day, and it doesn't need them at nighttime. It could allocate that energy to other processes. So here's the basic of what the rhythm will look like. The top graph here, so that's your behavioral or physiological rhythm. And let's just say it's photosynthetic proteins. Or actually, well, in this case, it's something that's peaking at nighttime. So we'll get to that in a second. But anyways, it peaks, the internal rhythm up here peaks at nighttime, and then the below is the environmental cycle. So you could kind of line them up, and then it kind of goes down into a trough during daytime. To go through a full cycle from a full wave pattern, it's just a standard sine wave, that's called the period. So that's a period of your cycle. The peak plus trough, that's the full amplitude. So that's the change of your cycle. So like wake and sleep. So, your attention span can be fully low when you're asleep and then fully higher when you're peak during the day. Now, for circadian rhythm analysis, how we know there's this internal rhythm and it's not just being put on by these night and day cues is they'll put the animal or the plant under continuous conditions that don't change. So here I just put constant light. And they find that the rhythm continues independently of these environmental cycles. So it still keeps going. Practically, what really happens is the rhythm significantly dampens. So you need pretty sensitive equipment to see it, but it has been proven, and it's a common thing. And this is called the free running rhythm. If you were to just put yourself in continuous light and nothing's ever changing, you don't know when day or night is, you would still have a mild rhythm. Then what happens, let's say it's the plant, and we put a pulse of blue light, just a short pulse of blue light. That would cause a phase shift. So it would shift where that period starts. And that shifts the timing, the internal coincidence with the environmental cycle. So that's how we could kind of play with the circadian rhythm in a greenhouse, is we could start to do these pulses of light, and also temperature pulses work too. So there's literature showing that, oh, if you do a heavy temperature differential between night and daytime for tomato, that helps with photoperiodic injury. So I wanted to see, well, can you do the same with light? And there is some literature showing what light qualities and stuff could help alleviate photoperiodic injury. But really, this is what's at play. It's not necessarily the light quality itself, it's how you're inducing the rhythm and how you're moving it. So here's a little video. Hopefully this plays. Uh-oh. Maybe I clicked it too many times now. So this little video is a tomato seedling that's been imaged in a time-lapse image by this research group, by GrowON, and I actually met them. And so they're like some of the leaders in the circadian rhythm research for plants. And so they developed this algorithm that looks at the pixels on the screen, and it could tell which pixel is a leaf pixel. And the time-lapse images go by, and it's able to create these vectors. So the speed at which those pixels are moving up and down or side to side. Oh, I see it. I see it.
I just have to take
the pointer off. Okay. So here you see it. This is over 5 days. Every single day, every 24 hours, they're coming up and down, up and down. And you want to analyze the circadian rhythm for about 5 days. And this is under continuous conditions. There's no light change, no temperature change, no watering change. This is just naturally in this tomato plant. And so you can assess all the circadian rhythm traits from this data. So the free running period under constant conditions, that natural oscillation that we just seen in the video, that's actually usually above 24 hours, but we have 24-hour day-night cycles. So the circadian rhythm is always just kind of a little bit longer. And what they found was that free running period, it correlates with the latitude of origin of that species in animals and plants. So it's called the latitudinal rule. If you start at the equator, you'll have an organism with a 24-hour period, free running period. But if you go all the way up north to like Alaska or Northwest Territories, you'll have like a 26 or 27-hour free running period. And a good example here that they did in a study, so it was done in tomato too. They found that tomato follows the latitudinal rule, but a good way to look at it is soybean. So some of us are familiar with soybean and how they have different maturity zones. And, you know, there's soybean grown in the equator, there's soybean grown all the way up in Ontario. And each of these zones moves north. It kind of shifts around on the map, but there's this general latitudinal gradient in these maturity zones. What they found in their study was that each of those maturity zones, it correlated with latitudinal gradient, that free running period. They analyzed all these soybean seedlings with that software. And they found that breeders, while they're breeding for maturity, they're breeding for yield and all of this, they inadvertently bred for circadian rhythm traits. They weren't even looking for that, and it just naturally happened. And so it's in wild plants and it's in bred plants. And what I'm suggesting here, because I hear that there's some breeders that may be here, I'm suggesting that if we're in a greenhouse system and we're artificially increasing the day length in this greenhouse, we should probably be looking at these circadian rhythm traits and select for cucumbers and tomatoes and peppers that have these longer free running periods that could sustain supplemental lighting over, you know, longer durations. Now that's adaptation. Before I said acclimation, we could control acclimation. We could control the circadian rhythm and how phase shifts. but adaptation is just what it inherently has. And so some cultivars are more tolerant than others. And I bet you if we did a big experiment on it, we would find this correlation. So all of these free running periods, though, they always have to be phase shifted back to 24 hours. The longer the photoperiod, the longer the circadian rhythm period, the greater the phase shift that's required. So here's an example. We've got a little day-night cycle. Let's say this is at a latitude that has 14 hours as the longest day. That circadian rhythm, regardless of it being winter time or like whatever, fall and spring, which is 12 hours, but it's adapted so that it could handle that 14-hour day for its photosynthetic proteins, let's say. And let's say that period, so it's more than 24 hours. Let's just say it's 25 hours there. Here's another example. Further north, you would have an 18-hour long day. So that plant would have to have its photosynthetic proteins able to last in a peak phase for that full 18 hours. So it would need a longer period, and it would also need a greater phase shift to keep on bringing it back to 24 hours to be in resonance with the environment. So these are some basic concepts. It's called the art of entrainment. There's a pretty great Roenberg there at the very bottom. There's a great resource that talks about the art of entrainment, and they're actually talking about animal systems, but it's plants and animals are very similar in this regard. And I'll take questions at the very end because I did kind of fly through a lot of concepts there. But here's part one. So these transpiration rhythms. Now that we got a little bit of an idea of what we're doing. So the methods, we focused on completely controlled environments. Here we've got the Biotron whole plant system. You can see we have high pressure sodium lamps and an LED lamp there. There's 6 independent chambers. Each we can control the humidity, and we can control everything, the temperature independently. And what it measures is the net carbon exchange rate. So basically photosynthesis and whole plant transpiration or respiration. And that's kind of your carbon budgets. And it also measures transpiration. So if you could kind of see in there, those tomato plants that are tucked in there, they're all on a weigh scale. And so the plant loses a lot of weight as it's evaporating, it's transpiring. So we're able to quantify how much transpiration is happening on that whole plant level. And recently we installed an irrigation system. So this system, usually it was used for maybe a couple days at a time. Now it's used or can be used for 14 days without opening. So we can really assess these transpiration rhythms. And I found about a 5-week-old plant, like, that's about the max that these can hold for tomatoes and cucumber. Well, cucumber a little bit less because they get pretty big quick. Here's what this dynamic LED recipe looks like. So here we've got on the y-axis, we've got light intensity. I'm going to need my little thing. Anyways, you know what? Maybe it's okay. We've got, oh, we got to go there. Okay. Perfect. Laser pointer. Okay. So we've got light intensity, and then we've got the hour of the day. The dark shaded bars are nighttime. The light shaded bars are daytime. And we see here on the first day, there's nothing special. We've got a high pressure sodium lamp and an LED. They're at the same intensity, and they just come on for 12 hours and then they shut off for 12 hours. So that kind of starts you up. This is a classic way to assess a circadian rhythm. You just start with 2 normal days or 2 normal nights in a day. And then on the first day, we step in, and the high pressure sodium, we just start there. It just stays the same. It stays 200 at all times. We can't change the intensity of the high pressure sodium. It's meant as a control. Under constant light, what happens to the circadian rhythm? Now with the LED, we get back to that 200 intensity for a couple hours. Then boom, we blast it with a whole lot of actually, before I get to that, that day spectrum, that's the spectrum you see here. Just a normal white with some supplemental red, just a standard grow spectrum. And then boom, we blast it for a couple hours in the morning with a lot of blue light. So then that's the spectrum that's coming there. And then at nighttime, so these shaded bars here, I just kept the bars there. That's meant to indicate subjective night. So technically the lights are never coming off, but it just helps us keep track. You see there's like 6 days here. And so the spectrum for the LEDs at nighttime is a dim blue plus a bit of far red. And so that's what was being researched at the greenhouse level at Harrow. And so we're just kind of mimicking that. The only thing different that we're really doing here is adding this blue pulse light, because I believe that's very critical to entraining a circadian rhythm under constant, like completely controlled system. And so here's the transpiration rhythm. There's other data, but this is the most important thing to get across here. So the same spectrum that we just seen, now we're looking at the actual transpiration rates of those two plants. At nighttime, it's pretty low. It's not zero, plants still transpire at night. And then during the day, it comes up. We see the LED plant is a little less. In this case, this plant was actually just like a little bit smaller, I think. And the HPS, it transpired a bit more compared. Then they go through another night, they go down, and then they come up. And then here we see something different right away happen with the LED. Boom, its transpiration peaks much higher than it was the previous day. The high pressure sodium is only a little bit higher. And then check this out. This is what gets really cool with the circadian rhythm aspect. So look at that yellow line. That's the high pressure sodium. Its transpiration drops after 12 hours going into the subjective night. The light didn't change, temperature didn't change, nothing changed. So that's how we know that's a circadian rhythm. The stomata on the plant, they were closing because they were expecting it to be nighttime. But then all of a sudden, it wasn't nighttime. And so they get caught halfway open. So they're not all the way closed like they would be at nighttime. They're just kind of half. And then over the next few days, they kind of increase. There's no obvious rhythm. The data is a little too noisy, so I can't assess free running rhythm using this system. I've got some modifications to try to improve it. But for the most part, what we can say is that under constant light of high pressure sodium in this case, yeah, that first day, clearly there's a circadian rhythm. It was wanting to close and do its nighttime thing. We interrupted it, and then that dampened the rhythm so much that we could hardly detect it. Now, if we look at the LED, the transpiration comes lower, which is normal. It was a dimmer light. It had a bit of far red. Far red induces stomata to close. Blue light induces stomata to open. So that's good. It brings it down. And then the next day it brings it up, brings it down, brings it up. Now, you might be asking here, well, okay, is this circadian for the LED? Or is it what in the circadian literature, they say masking. So they say, oh, if you're giving a pulse of light and it's responding to a pulse of light, well, then that's not circadian. That's just a normal response. How we know this is circadian, aside from proving it with the high pressure sodium there on that first day, but we can see, look at those red lines there. So during subjective night of these dynamic LEDs, the light intensity is not changing at their subjective night. That's dim blue and dim far red. However, transpiration is increasing at night. It's pretty linear, and it's pretty consistent day to day. So those stomata are opening before the subjective sunrise. They're anticipating the next day. So that's what shows us it's circadian. And when I do analysis for this, there's a special algorithm for entrained rhythms rather than free running to assess the details of that. But that's what really drove a lot of inspiration and further questions and further experiments to do to really look at this effect that's happening with these dynamic LEDs and transpiration rhythms. And just to show here, we've got those plants that were in those chambers for 14 days under continuous light. The high pressure sodium, you see there's some chlorosis there. I've got the leaf number labeled. So L1 is just the first leaf, L2, L3, L4, and they were a little bit more than L8. So of course, L1, yeah, it would be senescing. The older leaves generally just die back over time. But compared to the LED definitely still held on to its older leaves. And the high pressure sodium had that intraveinal chlorosis. It even had the marginal chlorosis on the L8. The leaves were crispy. They weren't like healthy. I'm sure they'd be more susceptible to disease. Whereas the LED, those are beautiful. Like I had to break the leaf just because they were kind of, to get them flat. So that's not the leaf's fault. That's me. But they're green. They look beautiful. Even the L8, everything's great. So that is a beautiful, healthy plant. And then what I do is I'll take that transpiration and I put that in a circadian rhythm analysis. And we could take out the effects of growth because every day it was increasing in leaf area and evaporating more or transpiring more. So this way, now we could just assess a circadian rhythm and we could compare different LED treatments with that. So that's the future direction. We're going to be doing more of this. We're going to change the phase at when we apply that pulse and change a few different aspects of it. So what we learned is circadian transpiration rhythms, they are entrained by this dynamic LED recipe. And how we knew that, the transpiration increases prior to the subjective sunrise. Now, why is that important for the bigger picture? I think this is useful for winter greenhouse production, and there's even controlled environment growers. So this is useful for controlled environment growers, just to keep a healthy rhythm that the plant is in total resonance with everything you're giving it. But in the winter, like this last year, we had several consecutive cloudy days. And then what happens in early March after a week or two of cloudy days, all of a sudden you get this super bright sunny day. Well, then that plant is going to be struggling a little bit in the morning because it's not used to that huge blast suddenly, and that affects its energy balance. So the energy balancing, a little bit of background for those who aren't aware, I'm sure all the greenhouse growers know what I'm talking about here. It's the amount of energy input into the plant and into the greenhouse environment itself must equal the output energy from the plant and from the greenhouse itself, or else you'll get a crazy heat buildup in the greenhouse or whatever. So on a plant level, the plant takes in this energy from the sun, and then through evaporative heat loss, it turns that energy it's getting into latent heat, puts it in the water vapor, and then you vent that out of the greenhouse or wherever. And that's how you maintain the whole energy balance. So during sunrise, like I've measured it, sunrise happens very quickly. Within an hour, you go from 0 to over 1,000 ppfd. And so that creates a huge input energy into the crop that the crop's got to deal with quick. Stomata are actually kind of slow to open. So if you had these dynamic LEDs, we could wake the plants up early and they can anticipate that morning requirement to evaporate a lot. And this isn't on its own either. This could be combined with existing strategies. Greenhouse growers already deal with this. What they do is they'll maybe increase the temperature of the root zone a little bit, just so that the roots are more active and able to take up water faster. They'll maybe do some other strategies to get ready for that energy balance that's going to be needed very soon. So I suggest these dynamic LEDs, they should be in resonance with the whole system. Everything should be working together. Like, oh yeah, and you also irrigate right before sunrise or right when it's needed. So part 2, here we did very similar dynamic LED strategy, but I changed the photo period. Instead of 12 hours, I tried to push it to 16 hours. instead of blasting that much blue, I tried to go with something a bit more practical. I only increased it by like 100 ppfd of blue light. And I grew tomato and cucumber in fully controlled biochambers. So this is not in a greenhouse. So with the tomatoes, they were about 5 to 6 weeks old. And we found the control is right here next to the dynamic. And then we did the constant light if you just didn't change the light intensity. These are all the same DLI. They're even the same DLI of far red light. So if you just calculated the amount of far red light I gave at nighttime for the dynamic, but not during the day, whereas the control had just a little bit throughout the day, and same with the constant. Everything's equal on a DLI level. And the blue light, I tried to get it as close as possible so they all have similar-ish blue light on a DLI level. So statistically, the stem length was greater in dynamic. Control and constant, they weren't that much different. The leaf area was increased under the dynamic. The specific leaf area, so now we're including the leaf weight to leaf area. That wasn't different between dynamic and control. So that means that the dynamic didn't make these big spindly leaves. Like they were still the same thickness, same substantialness, because if you put too much far red, you could encounter diseases and your crop is more prone to disease. So it didn't experience that problem. Constant light, on the other hand, had much heavier leaves. Total biomass was significantly higher in the dynamic LED and significantly lower in the constant light. And that's to be expected. Obviously, the constant light tomato plant, it wasn't enjoying that. They did have photoperiodic injury on them, but I needed them as kind of like a comparison. And so the cucumber, interestingly with the cucumber, it was not statistically different between control and dynamic, but constant was always lower. So they're not totally tolerant, that's one story. But control and dynamic, they had the same total biomass, the same height, the same leaf area. But what's interesting is that the dynamic had a higher yield. Now this is 5 to 6 week old cucumber plants. This is the first yield. This isn't like a sustained greenhouse level yield. That needs to be shown in future experiments. But I believe it's quite promising to see this at this level, that we had significant effects, that the dynamic treatment had a higher yield of cucumbers than control, and constant obviously had less. Not only that, it had a higher yield, and if you could kind of see in the picture there, these tomatoes or these cucumbers are a lot greener. They look really nice compared to the control. So it's a higher quality. I didn't quantify quality because I wasn't expecting that. It's been shown in Zhu Ming's past work that, yeah, if you supplement with more blue light, you'll get nicer cucumbers that are darker green. But here we only supplemented with a pulse of blue light. And we actually restricted blue light so it wasn't as much in the rest of the photoperiod. So a pulse of blue light is sufficient to get that nice color. So not only are we getting transpiration, we're getting quality. And the harvest index, remember, they were the same total plant biomass, but dynamic had a higher yield. Therefore, it has more fruit than total biomass, so the harvest index. That means that the plants are more generative. So that vegetative to generative balance, this is a major point that I was not expecting to see. And then, although it's not significant, the harvest index for the constant light was lower. So it's like under the constant light, you get a more vegetative balance, and under the dynamic light, you get a more generative balance. And it's not like overly generative where you lose out on total biomass and everything. So it's not weakening the plant. It's like a sustainable generative behavior. And so another telltale sign that this is the vegetative to generative balance being affected here is the dynamic light had less of the leaf mass fraction. So if you look at the amount of leaf to total biomass, the total plant carbon budget partitioning between organs, it had less leaf mass fraction, which means it was throwing that more into fruit. That's by definition vegetative to generative balancing. And constant light was a little higher, but not significant. I think we just need more data to get the significance. So a little bit of a take home, constant light. I know it's not significant, but it still kind of looks there. I'm not excluding this possibility that constant light induces vegetative balancing. And I believe it's just not significant because just the yield and biomass in general were lower under these conditions, but there seems to be a pattern. Dynamic lights or dynamic LEDs, they definitely significantly induce generative behavior. We know that because of the increase in harvest index and decrease in leaf mass fraction. And it was a higher yield without compromising vigor. So there's also the plant canopy architecture, so the morphology. And I noticed it was weird that cucumber and tomato, they respond very differently. I was expecting they would kind of respond similar, but no, they're pretty different. So here's the stem mass fraction, the amount of stem. We've seen that the tomato was significantly taller. Obviously, it was partitioning more energy into the stem. The cucumber, it wasn't significantly taller, and it's not significantly putting more energy into that stem, and it doesn't even look like it. But constant light and the cucumber, it seems it's a little higher, not significant though. And in the tomato example, I think why that stem mass fraction was higher was because you notice like a vegetative plant, they get the really thick stems. I think that's what was happening, and that's why we had more partitioning there under constant light. So the petiole mass fraction, this is what totally distinguishes cucumber and tomato. Cucumber, they, instead of growing taller, they move their petioles out further. So they have the same leaf area, but they're changing their canopy architecture. So I'm curious to see how this could be played with on a greenhouse level. Whereas tomato, it decreased the petiole mass fraction. And that's because I think tomato, it's a compound leaf. It has stem in its leaf, you know, like it's part of it. So I think it treats it in a partitioning way the same as a leaf because it was decreasing that. But cucumber, I don't know, I thought that was interesting. It's putting more into petioles rather than stems. And they were longer, they're much more substantial. Not like overly large, but they looked bigger than control. And so here's the leaf mass fraction. I kind of already talked about that. And so in both cases, tomato and cucumber, they're taking in the dynamic, they're taking that vegetative partitioning and putting it into generative. Although the tomato, I don't have fruit yield data, so I can't say that. And then I think it's just less for constant light, mostly because they were getting photoperiodic injury. So future direction and visions. I see there's kind of three pillars of plant responses to LEDs. There's this, for your normal grow spectrum during the normal day, especially for the indoor growers, you want to focus on like a full spectrum. That's like your main photosynthesis, your main yield determiner. That's where your photoperiod, most of your DLI is going to come from. And you're going to want to make that as electrically efficient as possible. So you're trying to push that photoperiod as much as you can while still kind of accounting for the whole canopy. And there's some new research on increasing the amount of green light in the spectrum for a large canopy helps the whole plant photosynthesis. So that's the category that would go into your normal daytime full spectrum. Then you have this blue. So blue, and we're talking here just that blue pulse. You just need a pulse of blue light. That makes the plant more compact if you want it. Some ornamental growers would want something like that. and other industries. It induces the stomata to open, and it also increases the phytonutrient and antioxidant contents. So there's data on that from other literature, but just even in my data, like you could clearly see the cucumbers were nice and green. So that's that phytonutrient content. And then the far red data, or the far red part of the whole spectrum, it makes a plant more elongated, which is in direct contrast to the blue compact. So there's this interaction between blue and far red that you have to balance. It makes a more open canopy architecture, and it does induce the stomata to close. So that's where the circadian thing comes in, is that you need to be cognizant of the timing of far red and the timing of blue. So my future direction here is I want to try to do what's called phase response curves and the interaction response curves between the blue and far red. A lot of people are working on the full spectrum. We could draw data from elsewhere on that, but it's mostly these blue and far red interactions with the circadian rhythm and overall plant morphology and canopy architecture, I think is a good place to go. Now there's different types of programmable dynamic LED control. Right off the hop, this has been done for a long time, auto dimming. The light in the greenhouse gets to a certain level, you bring it back, you just shut your lights off or you dim them. Because it's not beneficial to give more light while the light's already pretty strong. There's kind of a saturation point of the curve there for photosynthesis. After that, and built into that, you have your circadian rhythm entrainment. This is a daily program that does what I just talked about. It gives this pulse of light, gives a normal day spectrum, and then it has this night spectrum that's dimmer. And that's useful for helping the energy balance. It helps the plants endure longer photoperiods so you could get more electrical efficiency. And then built on top of that is that not like that circadian rhythm entrainment, it doesn't always have to be the exact same intensity of blue in all of this. We could actually change that amount if we have a truly dynamic LED fixture. So we could do what's called phenological staging. So depending on the life cycle of the crop, let's take lettuce is a great example. So, and this is true even for transplanting tomatoes, first time when they're in the greenhouse, or transplanting cucumbers. Early on in their development, you want to try to give more of that far red at the right time. And you want to try to expand the leaves, expand the radiation capture so the plant could grow faster, quicker, and fill canopy as soon as possible, or reach the high wire as soon as possible. After that, you could hold back your far red, and you could focus on something like establishment or your normal cycle, and then maybe it'll go back into a normal cycle. But then for lettuce specifically, and it's also been shown in tomato, maybe you want to boost the quality of the fruit or the lettuce, and normally they would use blue light. You could use blue light for the whole growth of the crop, but you're missing out on yield because blue light makes the plant too compact. If you just apply it for 5 days before harvest, you could up your antioxidant components and everything without impacting your yield. So you get that quality and you just kind of do that final thing. Now, another important kind of contribution in this phenological staging is the grower could also kind of just see how that cultivar responds. Some cultivars aren't that sensitive to far red. Some are very sensitive to far red. There's a whole spectrum depending on what's available. Every year there's new cultivars coming. With a truly dynamic programmable LED that, and what I'm trying to promote here is like a universal kind of level, is you could use that same fixture to just fine tune for your new crop. Maybe even it's a different species. Maybe you're switching to strawberry or something. You could use the same LED for a totally different species or even a different cultivar with these same principles. You're just changing the dosage and timing. So I'd like to make my acknowledgements. Thank you, Bernie, for letting me break things in the lab. Thank you, Demos and Nahid, for so much technical assistance. Thank you, Zhu Ming and Jason, for all of your inspiration and help. Thank you, Barry, who gave me a lot of circadian inspiration, the University of Guelph Plant Agriculture Department, They house my madness. And the OGVG, BSF, OMAFRA for funding the project, and Genoptic Inc., they supplied some of these LEDs for these experiments, which are very difficult with traditional LEDs to try to do. So thank you to them too. We'll go to questions. I didn't go over time, did I?